Good afternoon and welcome to the Biomedical Data Science online session program with the Texas A&M Institute of Data Science. My name is Christy Retzer and I'm the program coordinator for the Institute. Our speaker today is Dr. Sutanoy Dasgupta from the Texas A&M Department of Statistics, who will conclude his last session on statistical learning. Today, he will talk about dimension reduction. The materials for his previous session 6 on clustering are available on the program website, where videos of this session will also appear soon. The Biomedical Data Science series has monthly 2-hour online sessions aimed primarily at graduate students in the biomedical sciences, but is open to everyone interested in the area. From the description on our website, you'll see that the sessions cover data science topics, statistical learning and computational methods, big data systems, data management, fairness, privacy, and policy, all with an emphasis on biomedical context and applications. The first 6 sessions in the series comprise recorded materials, a primer in R and statistics, and 2 sessions on manipulating data in R that were previously given in the related super fun big data series, which some of you may also be attending. The materials for today's sessions are an R notebook that integrates the exposition with code examples. Dr. Dasgupta will present this in the Zoom session. You can view your own copy of the notebook through the link to open them in a browser window in Google Colab. In the email about Zoom registration that you received yesterday, also on our website. If you're logged into a Google account, you can run the code examples in the notebook and alter them during the exercises. We do recommend you do this. The first time you run a code block, clicking at the arrow at the left of the block, you'll be prompted to allow it to run. To allow, click on Run Anyway. Please consider participating in the post-session survey, an email which will be coming to you shortly after the conclusion of today's session. And that email will be coming from Sean Hutchins, and you can see his email on the screen. TAMIDS has contracted with the Texas A&M University Education Research Center to conduct an external evaluation of program participants' perception of their competence in data science. As part of that study, TAMU ERC researchers will conduct surveys throughout the Qualtrics online survey platform for each session. The purpose of the survey is to help us determine the effectiveness of our program sessions and the subsequent impact on your confidence in data science. TAMU ERC researchers will share information with our team only in the aggregate and non-identifiable information collected as part of the study will be shared with TAMIDS Biomedical Data Science program project personnel.
Welcome to today's session, and today's session is going to focus on dimension reduction, but we're going to start off by talking about k-nearest neighbor classification. This was a topic that could have been covered during the classification session, but we covered other topics and we left it for the last session. So let us first go through that, and then we're going to talk about dimension reduction techniques, which is the focus of today's lecture. So, k-nearest neighbor classification. Remember that classification is supervised learning. So when you have the data, you also have, for the training data at least, the right answers, the right labels corresponding to the features. The idea of KNN, where NN stands for nearest neighbor and K is a number, right? 1 nearest neighbor or 5 nearest neighbor or something like that. The idea here is that birds of a feather flock together. That means if you look at this picture, the idea is that if you have a spread or a scatter plot of data points, the data that are clumped together or clustered together belong to the same label. As you can see in this plot, the red labels, the green labels, and the blue labels seem to be clustered together and separate from each other. Of course, there are some outliers or points that do not conform to this idea. For example, there are a few blue dots in between green dots, but no data is perfect, right? So the idea of this algorithm is that you have a test data point and you have all these training data points, right? From the test data point, find the distance to each of the training data points and identify key points among the training data points that are nearest to the test data point. And then look at the labels of these k neighboring points because you know them. Remember that this is label data. Now, suppose k equal to 1. In that case, it's simple. You find the training data point that is nearest to the test data point, and whatever the label of that training data point is, you assign it to the test data point, and that becomes your predicted label. However, when k is greater than 1, sometimes you can run into issues like ties. So here is a performance of 1 nearest neighbor on the left and 5 nearest neighbor on the right. The trouble on the right-hand side is these white patches where the algorithm couldn't figure out how to label the test data points. Right here, the problem is, suppose you have 5 neighbors, 2 of them are red labels, 2 of them are blue labels, and 1 of them is green labels. That's a tie. How do you decide which label to choose? Well, in that case, the strategy usually is to reduce the k. From 5, you move to 4 k nearest neighbor, so 4 nearest neighbor, and then repeat the algorithm. And if you still end up with a tie, you keep going until you reach k equal to 1, where with probability 1, you are going to find a unique answer. Now, to formalize this concept that we talked about, let us go through these 3 steps here. So given a positive integer k, which determines the number of neighbors that we are interested in, and the test observation x0 that you would like to label, the KNN classifier first identifies the k points in the training data that are closest in some sense to the test data point. That could be Euclidean, that could be something else, depends on the metric. Now, once you have these neighbors, then we find the conditional probability of each label given the data. Well, this is just a mathematical term of saying, suppose there are 5 data points, so k equal to 5. If 2 of them are red, then the probability of the red label given the test data point is 2 out of 5. Because there are 2 out of the 5 belonging to that class. Similarly, for the blue label, it's going to be 2 out of 5. And for the green label, it's going to be 1 out of 5. That's basically the posterior, the conditional probability of class J. Now, once we have this probability of each of the classes, given the neighbors, given the test data point, then you can find the class with the highest probability. And we know what to do with respect to ties, right? We change the k. So in general, how do you select the number of k's? Well, we have talked about cross-validation, where we split the training data into further subparts, say 10 subparts. And then we pretend that one of the 10 subparts is a test data set, and we try to predict the labels for the test data given the remaining 9 out of 10 of the parts of the training data. And then we do it for each of the 10 parts, and we see which value of k gives the best results. And that is cross-validation in a very non-technical description. Remember, though, before applying KNN classification, you need to normalize the data. The reason you have to do that is that we are trying to find the neighbors using the concept of distance, right? So think about the most common distance, Euclidean distance. If we have features that have different units, then while trying to calculate the distance, one of these features might completely wash away the effects of all the other features. For example, we have two features, blood pressure and RBC counts. Well, blood pressure ranges from 80 to 140, where RBC count ranges from 4 to 6 millions. And if we don't take into account these different units, we were going to run into trouble. All the distances are going to be affected by the RBC counts, even though the blood pressure ranges might be very different. That's why we should always scale the data. Now, the reason we center the data is slightly different and a bit more involved. The reason is when we have, say, several data points, several samples, several observations, we want all the observations to be equally important. However, if we do not center the data, in some cases, it might give into problem that it gives to what is called data hubs, which are samples which are centrally located, and that's why they affect the nearest neighbor of a lot of other data points. And so these points that are in the nearest neighbor of several other points become very influential points, very much more influential than some other points. And it has been shown through research that if you center the data, then this differential effect of some data points of these hubs gets taken care of. So whenever you perform k-nearest neighbor algorithm, make sure that you center and scale the algorithm, also called normalizing the algorithm. Now I'm going to talk about an example. We are going to use the IRIS data set that we have used several times before. So to normalize the data set, I have used a user-defined function. Remember that we use the keyword function followed by the keyword x. Well, a list of a bunch of keywords. In this case, we just need one keyword x. And then we define the operation within the function that we want the function NOR to do, which is normalizing. That means we subtract the mean of the data and divide by the standard deviation. Now, so note that this input is going to be a vector, right? So we take the IRIS data. Remember that we don't need to load the IRIS data. It's already loaded in R. So, and we take the first 4 columns, because remember that the 5th column is the response. That means the species. The lapply function applies the function NOR to each of the columns of IRIS. That's the idea. That's the function of the lapply. So each of the columns of IRIS is a vector, right? And we apply the NOR function. That means we normalize each of the columns of the IRIS data set, and then we convert it to a data frame format, because the subsequent steps would require that. So remember that. So notice that once we look at the summary of the normalized form, we note that the mean of all the variables is 0, right? Next, since we're doing a classification problem, we are going to split the data into training and testing. And then we are going to use the KNN function in the package class. So we're going to install the package and load it. And then we're going to run the KNN classifier. So for the KNN classifier, we are going to use the training data set, the test data set, the labels of the training data set, and the value of k for the k-nearest neighbor. So remember that IRIS target category is nothing but the training labels, the true labels corresponding to the training data set. So based on that, we have stored the KNN object in a variable PR. And then we can combine using the table function to compare with the actual categories and the predicted categories. And we see that we have a pretty high accuracy of 93.3%. So there are many ways to find this accuracy. In this case, I have used a user-defined function just to get you used to using user-defined functions. So this is basically the number of diagonal elements. That means these are the correct ones divided by the total number of observations. All right, so first of all, we have a quiz now where we are going to talk about the properties of KNN algorithm. So read the three options and try to see which one of these looks wrong or false. So I would ask, yeah, so the quiz is loaded. So take a couple of minutes, try to think about the question and see if you can answer it. All right. Thank you so much for participating. This was a very conceptual question, and let us try to go through each of these options and see what's going on here. First option, for a large value of k, points from other classes may be included in the neighborhood. Well, that makes sense, right? Because if we have too many observations, then it's very possible then that observations that belong to a different class might also become a part of your neighborhood. The more interesting question is, for the very small value of k, the algorithm is very sensitive to noise. Let's see if that is true. Let us try to look at this picture, okay? And specifically, look where my cursor is. This area is under the green label region, right? Now, but look at this blue dot here. That's clearly an outlier. That's clearly a noise. That's not supposed to be there. But if you have a test data point that's very close to the blue data point, and if we use only one nearest neighbor, then it gets only affected by the blue data point. Whereas it should make sense that it should be in a green label because it's near the green region. So it is true that if you use too few observations in your neighborhood, then those particular observations will completely influence the prediction performance, right? So if they are outliers, if they are noisy, for noisy data, if those points are not the correct label, you might have a wrong prediction. But if you use a few more data points, then the effect of each data point gets more averaged out because you have more information. So basically, the idea of trying to find k is trying to find a sweet spot is between using too few and getting affected by noise, probably, and using too many and then having too many observations there and getting affected by observations belonging to different classes. So right here, if you see that if you increase the K to 5, then you will find that there are, say, 4 green points and 1 blue point, and your prediction will be green, which is what we want for this region, right? So here is the idea. So if you see this blue patch here, if we had a point there, then even though the region should be green, we see that we would have predicted it to be blue. But when we take 5 nearest neighbor, we correctly predict the entire region to be green. All right, next. KNN is used only for classification problem statements. Well, because that's the only remaining option, we know that it's false. But why is it so? Well, it so happens that you can even do regression using this approach. So even when your response is continuous, you can just say that, hey, based on the training data, I'm going to find my, say, 5 nearest neighbors, look at their corresponding responses, and take the average. And that is going to be my predicted value for the test data point. That is how you do K nearest neighbor for regression. So it is not true that KNN can only be used for classification. It can also be used for regression. All right, so that brings me to the end of the makeup topic that we were supposed to cover in the previous lecture. So before I move on, I'm going to pause for a couple of minutes. In those 2 minutes, you are welcome to ask me any question regarding this topic. If you want me to revisit any explanation or elaborate on something, you're free to ask. I'm going to wait a couple of minutes, and then we're going to take a 2-minute break, and then we're going to move on to the next section, next section. Right, it's if all of you are good with this topic, then let's return at 1:27 p.m. and we're going to resume talking about the next section at 1:27 p.m. All right, let's move on to the next topic. So in the next part, we're going to talk about unsupervised learning. And specifically, we're going to talk about the curse of dimensionality. And we are going to look at two approaches to dimension reduction. All right, so what is curse of dimensionality? The idea is, the very basic idea is, as the number of features increase, you need exponentially more data points to have a meaningful result. And having exponentially many data points is not a good idea all the time. It's not possible, it's difficult to handle. And that's the curse of dimensionality. So think about it. Remember that for any statistical method to work, for any dimension, you need to have at least 5 data points. That's the rule of thumb. So think about it. Suppose you have 2 features which has 3 different levels each, right? So if you want to do prediction for each combination of the 2 features, so suppose you have colors, red, blue, green, and you have, say, species 1, species 2, species 3. And if you want to do good prediction, you need data on all the combinations. So red species 1, red species 2, red species 3, all the colors. So there are 3 square number of combinations. Now imagine that there are 100 dimensions. Think about the number of combinations and the amount of data that you are going to need to be able to perform any statistical technique. Also in sampling, the idea of distance falls apart. Euclidean distance falls apart in higher dimensions because the idea of neighbors breaks down because all the observations are too far apart from each other because of the dimensions. And you need tremendous amounts of data to even form a concept of neighbors. So that is the curse of dimensionality. So what do we do in that scenario when you have too many features? Well, we are going to focus in the scenario that there might be thousands and thousands of features, but all of them are not relevant to the problem at hand. All of them are not useful or important. So what we would like to do is, starting with say 10,000 dimensions, if we can reduce it to 100 important dimensions and ignore the rest, that's useful, right? That is the idea of dimension reduction. The first method that we're going to talk about here is called principal component analysis. So for principal component analysis, just look at these 2 pictures. Well, based on this picture, well, these 2 are the same pictures. They are not at the same scale, unfortunately. But this animal is a camel, clearly. But that answer is not very clear from this direction, right? Because it's hard to understand just from looking at this picture what kind of animal it is. But if you move aside and change the direction and look at the same object, you can identify it because you have more information from this side, right? And that is what PCA does. And that is the most important idea, that we change the direction from which we look at the same thing. And we change in such a way that we can capture most of the nuances of that object, most of the properties of that object, right? So let us look at this scatter plot. I have generated the scatter plot using this code, but you can have a look at it. But the important thing here is to look at this plot. So we have this x-axis and the y-axis. This is clearly a 2-dimensional data, right? However, do you think that x and y are correlated? Do they have any relation? Are they dependent? The answer is no. The reason is, simply from this scatter plot, I can see that the value of x changes quite significantly the value of y doesn't change at all. Very small change in the value of y, which means that the value of y does not really depend on the value of x. It doesn't care whether the value of x is +7 or -10. Its values, the values of y are very static with respect to x. So this would be a case of uncorrelated data, right? So in this case, can I say that here from this data, I can say that the y variable doesn't really change that much. So we are going to ignore the fluctuations in y and only look at the fluctuations of x. And we are going to make that approximation. We are going to assume that the y variable doesn't change at all. So we're going to flatten it. And we're going to say that only x is the variable that changes. So what we did just now is that we started with two variables, x and y, and we said that we are going to ignore the changes in y, and we're going to only focus on x. So we reduced the problem dimension. We are going to only focus on one variable x. Well, in that case, we know that x and y were uncorrelated and y wasn't changing that much. But look at this scatter plot, the second one. Both x and y change very significantly, right? X changes from -15 to +15, and y also changes from -15 to +15. And they are very strongly correlated, very strongly correlated. So we cannot say that y does not change significantly, because we can clearly see that both x and y change significantly. So what do we do in this scenario when the two variables are correlated? Well, let us see. Let us try to use this idea of changing the direction from which we look at the same scatter plot, the same object. So we have these original data points here, which are obviously correlated. Let us tilt the coordinate system and look at the same data points, but we change the direction from which we look at it. So now, if you tilt your head and look at this changed coordinate system, it is going to look like the first scatter plot. Only the coordinate system has changed, right? The new coordinates are not x and y, they are some new coordinates. But in that coordinate system, the new y-axis doesn't change that much. Only the new x variable, the new horizontal variable, changes significantly. So if we can tilt our view, then we can do dimension reduction. We can just ignore. We can first tilt our observation direction so that we look at it in such a way that the variables are uncorrelated, and that's why only one of the variable changes significantly while the other doesn't. So we can ignore that. And then we can reduce the dimension. We can ignore this blue axis and only have this deep blue axis and ignore the light blue axis. And that is the basic idea of principal component analysis. Before I move on to examples, any questions so far regarding PCA? Is this clear? If it is clear, then just type it in chat so that I know that you are comfortable with it. Or if you have any questions before I move on to examples, you can ask them now. All right. All right, let's move on to the examples then. So we are going to consider a data set called trees, which has 3 features. It has girth, height, and volume. You should remember that for PCA as well, we should normalize the data. We should center it and scale it for the very similar reasons. If we do not center it, the PCA, the principal components can get affected by the overall mean, but we will come to that later. All right, so we are going to scale the trees and center it using the scale function. And then we get the scaled and centered values of girth, height, and volume. Now we are going to use PCA to combine these three features into one feature. And that means we're going to reduce the dimension from 3 to 1. So what it means to combine features is that we are going to find something called the linear combination. Okay, a linear combination with, say, for features x, y, and z would be of the form some scalar number, some number times x, plus some other number times y, plus a third number times c, where these 3 numbers p, q, and r satisfy the constraint that p squared plus q squared plus r squared equal to 1. That means the sum of the square has to equal to 1. In this case, the p times x plus q times y plus r times z, this new variable is called a linear combination of x, y, and z. Remember that when y, for linear regression, we have y equal to ax plus constant. So the times a times x is called a linear coefficient, right? Similarly, we have 3 features with linear coefficients, p, q, and r, which satisfy some properties. So the function in R to perform PCA is called PRComp. And then in order to find this P, Q, and R, we do trees.pca because that's a variable that stores the PCA object. And then we do $rotation. Now this $rotation gives you the linear coefficients, these coefficients P, Q, and R. So the first principal component, the first variable, is basically 0.6085 times the girth plus 0.4891 times the height plus 0.6248 times the volume. That is the new variable. That is what we are performing by rotation. By rotation, we are changing the way we are looking at the data. Instead of looking at girth, height, and volume, we are going to look at 3 new variables, which we name PC1, PC2, and PC3. Now, PC1 turns out to be 0.6085 times girth, plus 0.4891 times height, plus 0.6248 times volume. PC2 turns out to be 0.4099 times girth, minus 0.868 height, plus 0.28 times volume. Similarly, the third PC. So if you go back to this picture, the original coordinate system corresponds to the original variables. The new coordinate systems corresponds to the PC1, PC2, right? PC1 is the variable that captures the most of the variability of the data. PC2 is orthogonal or is uncorrelated to PC1. That means these two variables have independent information. So whatever information PC2 has is additional to whatever information captured by PC1. So because they are uncorrelated, they do not have any redundant information that is shared between PC1 and PC2. And so on. So in this case, if you combine PC1, PC2, and PC3, you get back the entire information from girth, height, and volume. But the interesting thing is, unlike girth, height, and volume, which might be correlated, PC1, PC2, and PC3 are uncorrelated, which means that most of the variability is captured by PC1, some of the remaining variability is captured by PC2, and the last portion is captured by PC3. So if I ignore PC2 and PC3, I can still probably do pretty well, even with just using one variable. PC1, I can probably do pretty well. So that is dimension reduction. Instead of working with girth, height, and volume, which are 3 dimensions, we're going to work with PC1, which is 1 dimension. So with this intuition that the idea of trying to find a linear combination is simply trying to find 3 numbers and expressing the new variable in this form. So let us try to get a little more technical and try to understand the methodology of principal component analysis. So the point of principal component analysis is it tries to find linear combinations of input features that account for the largest variance in the data. Notice that in this scatter plot, the largest variance would be in this direction, right? And so that direction becomes my first principal component. The second direction becomes the direction that is orthogonal to the first dimension, but still captures the most information. Well, this is just 2 dimensions, so it's simple. So in higher dimensions, you first find a dimension that has the most variability. Then among the orthogonal dimensions, you find the one that has the maximum variability. That becomes PC2. Then among the remaining dimensions, you find the one with the maximum variability. That becomes PC3, and so on. So next, we're going to talk about linear dimensionality reduction. So suppose your original data has a d-dimensional feature. That means there are d features, right? And you want to reduce it to r dimensions. So r is less than d. In the above example of trees, d was 3 and r was 1. So a linear transformation is a transformation where you transform the original matrix to a new matrix. Well, this is just a mathematical representation of what we did here, right? I find a linear combination. So given the n observations of x1, x2 through xn, we have the data matrix, which has capital N rows corresponding to the different observations and d corresponding to the d features. Then with linear transformation, once we transform into a different data, we are going to have an n cross r data matrix. N cross r data matrix where r is less than d, which means that the new variable y, which is a linear combination of the x's, has lower dimensions. So we are performing dimension reduction. So to start off, let's just assume that R equal to 1, right? We are going to compress all the D dimensions into 1. So in the first case, the V matrix, the vector, the transformation vector is simply, in this example, this column. This is the transformation vector. So once you make the transformation, for each of the data points, we have girth, height, volume, but we have girth times 0.6085 plus height times 0.4891 plus volume times 0.6248, exactly what we've done here, to get one scalar number. So we started with 3 dimensions, ended up with 1. So while our x was n cross 3 dimension, our y is going to be n cross 1 dimension. So the first step of PCA is to center the columns. So we have to make sure that all the columns have mean equal to 1. So that is given by 1 transpose x. That is 1 transpose x is basically summation of xi. And we remember that the sample mean is just the summation of xi divided by n. So if summation of xi divided by n has to be 0, then summation of xi has to be 0, which is what we want. That's centering. So the reason we change the scales of the different data is, once again, like the case of k and n, we do not want the different scales of the features to affect the directions of variability. Because think about it, if we are looking at the variability of RBC counts, that's in millions. But if you look at the variability of, say, blood pressure, that's in tens. So it is always going to favor the direction of RBC counts, even though the values might be very similar in that scale. So we have to scale the data to make it uniform. We center it so that the PCA directions don't get affected by the overall mean. All right, so if we look at V transpose V, where V is this coefficient vector, then V transpose V is nothing but the sum of the squares of the elements. So it's going to be 0.6085 squared plus 0.4891 squared plus 0.6248 squared, something like that. And we are going to try to find V that maximizes the sample variance of the transformed feature. That means the sample variance of Y, subject to the constraint that we talked about here. That means in linear algebra terms, V transpose V equal to 1. So next, we're going to talk about a little quiz where try to think about the properties of PCA and see which of these 4 options seem to be a reasonable way to select the number of principal components K. I'll give you, say, a couple of minutes. Think about the problem, think about what we learned about PCA, and try to come up with an answer. So when you try to answer this question, think about it. We want to do dimension reduction, right? So we do not want to use too many principal components. That's the first idea. Second, we want to capture the variability in the data. The more variability we capture, the more information we have captured. So we want to maximize the amount of variability we capture while using as few variables as possible. That's the intuition of PCA. We don't want to lose information, but we also don't want to use too many variables. So that's the idea of PCA. All right, thank you so much for participating. Um, so let us try to go through each of this. Let us try to revisit the idea of PCA. So as we saw here in this picture or in these scatter plots, what we want to capture is the variability. The entire variability is in the direction, is in the diagonal direction that of the scatter plot. But in order to have this variability, we had to use two variables, x and y, right? Now, we want to explain this variability. So we do not want to use, we do not want to deal with something like this where you don't understand what the data is. We want to capture all the variability and understand the data. So we want to capture most of the variability, but we do not want to use two variables. In general, we do not want to use all the D data variables. We want to use as few variables as possible, but capture as much of the variability as possible. That's the idea of PCA. So think about it. Right now, we are using two variables to explain the variability of this data. But if I twist the coordinate axis and use these two new variables, that is this deep blue axis and this light blue axis, then if I only use the deep blue axis, then I have captured most of the variability in the data. Only this little variability that was captured by the light blue axis got ignored, but that is fine. I have reduced the dimension, but I have not lost too much information. That's the idea of PCA. So in general, the idea is that K is the number of principal components, right? So I want to use fewer principal components, but capture as much of the variance as I can, right? So, but if we use K to be too small, then you will not be able to capture the variability in the data. But if you use too many K, then, well, you are not reducing the dimensions optimally. So the right answer is I want to choose K to be the smallest value so that at least 99% of the variance is retained, right? So if I choose the largest value, then I'm unnecessarily using higher values of K to capture the same amount of variance. So if I can capture 99% of the variance in using K equal to 5, that means only 5 variables. Then I do not want to use 15 variables to capture 99.001% of the variability, right? That's why I want to use the smallest value K. That way, I'm doing the maximum possible dimension reduction. All right, let us try to, before I move forward, any questions about this concept, any part that you would like me to elaborate or revisit or re-explain? You can ask now. I'll wait for a minute, and then I will start talking about the applications using R. So take a minute to just absorb this information too, because this concept is very interesting. The idea of twisting the coordinates to find new variables that are uncorrelated and also capture most of the variability in the data. If you do not have any questions, can you just type it in chat that it's clear so that I can move on? All right. Perfect. Thank you so much. If it is clear, then I'm going to move on to an application. So if you are running this Google Colab right now, be prepared to spend some time here. It takes a while to install this package, okay? I have installed it before this lecture, but be prepared to wait some time if you're running it right now. All right, so the idea is we want to perform PCA on iris data. So first of all, let us try to split the iris data into two parts, training and testing. And first of all, let us try to plot the pairwise plots, scatter plots of the 4 variables: sepal length, sepal width, petal length, and petal width. For that, we use the psych package and we use the pairs.panels function. Right? So here on the top diagonal, you have the pairwise Pearson's correlation value. So the higher the correlation, the more correlated the two values are. So sepal length and petal length have a correlation of 0.88 because that's where it two matches. Petal width and petal length have a very high correlation of 0.96. Sepal length and sepal width has a low correlation of negative 0.16, but they are all significant correlation values. None of them are 0. So I can say that all the 4 features are correlated, which means that there is redundant information. So can we try to reduce the dimensions, but still have the same amount of overall information? So we are going to use the function prconf to perform the PCA. So this is another way to perform PCA while also simultaneously using the scaling and centering on the data. Center equal to T, scale equal to T. Now, once you have that, you get the rotations, right? You get the linear coefficients. So since there are 4 variables, you get 4 values. In the previous example with the trees, we had 3 variables, so we had 3 values. So PC1 is 0.52 times sepal length, minus 0.286 times sepal width, plus 0.57 times petal length, plus 0.56 times petal width. That's the linear combination. So you have PC1, PC2, PC3, PC4. Now, let us try to see. If we do the summary function, then we get a very interesting result. We get something called proportion of variance, which means it tells you the proportion of the variability in the data that was explained by the corresponding principal component. Now we see that the first principal component itself explains 73.63% of the overall variability, which is great. It's just one variable, but it could capture 73.60% of the variability in a data with 4 variables. PC2 explains 0.2199, almost 22% of the variability. But remember that the principal components are all orthogonal to each other. That means they are uncorrelated. So this 22% information is additional to the 73.60% that was explained by PC1. So if I combine PC1 and PC2 and look at the cumulative proportion, then we'll see that if I use PC1 and PC2, then 95.62% of the variability of the data is explained by just the first two principal components. If I use the third component and combine it with the first two, then I explain more than 99.5% of the variability. And of course, if I use the fourth one, I get the entire variability. So think about it. If we use only 2 variables, we are already reducing the dimension by 2, but only giving up 5% of the variability, right? So we saw that the original variables were quite correlated, right? We saw that they have some patterns in the scatter plot. But if we look at the species now, the principal components, look at their correlations. They're all uncorrelated. That means they all have separate individual informations. So each one of them have their own contribution. Also, these species are arranged in such a way that the first principal component captures the most information, followed by PC2, followed by PC3, and so on. So let us try to perform prediction, but only using the principal components. Okay. But think about it. We want to use some kind of a logistic regression. Okay. But when we studied logistic regression, we studied that the response variable can do only 2 variables, 0 and 1. But in this case, there are 3 levels, right? Setosa, Virginica, and versicolor. We cannot do logistic regression like that, right? But we can do an extension of logistic regression, which is called multinomial logistic regression, which allows the response to have more than 2 levels. For that, we use the nnet package, and we use the function multinom. Okay. So using this, we are trying to predict the species using the first 2 principal components, okay? And only on the training data. So we are no longer using the original sepal lengths and petal lengths, only PC1 and PC2. And let us look at the performance. And then we have an accuracy of 93.3%, which is pretty good, right? All right. So we have done a lot in this section. We have learned how to obtain the PCs. We have learned how to do a multinomial version, an extension of logistic regression, which is another classification technique or a regression technique. We have learned how to use the pairs.panel to look at the pairwise correlation when you have several features. So before I move any further to the next topic, I'm going to pause for a 2-minute break, but I'm going to give you 2 minutes to ask me questions on PCA. Does it make sense? Do you want me to explain some parts of the topic, or you have any clarifications? or is it clear? Well, that's good. That's good. If you do not have any questions, then we are going to stop for 3 minutes, just to take a break, and we are going to restart the lecture at 2:09 p.m. All right. So let's take a small break and restart the lecture at 2:09 p.m. Right, let's move on to the next topic, the next dimension reduction technique, non-negative matrix factorization. So there are different kinds of data that's been occurring recently, right? And most of the types of data can really overwhelm the classical analysis tools. So processing massive amounts of data requires really powerful methods for dimension reduction. So one particular type of data are data points where the inputs are known or constrained to be non-negative. For example, pixel intensities in an image, or amplitude, or occurrence counts. All these numbers are non-negative. So if you use usual dimension reduction tools like factor analysis or principal component analysis, or you do cluster analysis, they cannot guarantee to preserve this non-negativity. And so they are not always advisable. So this has led to a lot of research that can perform factorization or dimension reduction of non-negative matrices. And this has given rise to non-negative matrix factorization. So non-negative of matrix factorization has a huge amount of applications right now, from image processing to bioinformatics to signal processing to music analysis to portfolio diversification. So the idea here is that you start with a high dimensional matrix with non-negative entries, and then you sort of try to reduce the dimensions. So let us try to look at the method. The method is a little mathematical, but let us try to understand the concept behind it. So suppose that the original matrix, the original non-negative matrix that we had, which we call the target matrix, is called V. It is n rows and m columns. So n is the number of observations and m is the number of entities or columns. Now the non-negative matrix factorization means that we are going to represent this V as a product of two matrices, W and H, where both W and H are also non-negative matrices. Okay. Here, this V represents the data points, the W represents the latent features, and H represents the coordinates. But we're going to try to understand what this means. Let us look at this picture. So the original matrix is phi. The basis vectors are called W, and the coefficients are called H. So the idea is, the rank, the dimensions of this basis vector W is of the form n times r, where r is much smaller than n or m. So this r is the reduction from n or m, we go to r. There is the reduction in dimensions. So the idea is that even though we have so many entities, m entities, the concept here is that even though there are m entities, there are actually r important entities, and all these m entities are just linear combinations of these r entities. So we are going to say that, hey, there are m entities here, but actually there's actually r really important features, and these m are just combinations of these different features. So if you think about it, if you try to draw a comparison with the previous method, these are the original variables, right? These are the originals, and these are the principal components. Something like that, if you can think about it like that. And this matrix gives you the coefficients. So this tells you what is the linear combination. So if you look at the entity here, V, that is nothing but a linear combination of the corresponding row of W and the corresponding column, the coefficients. So it's H1 times W1 plus H2 times W2 and so on. So if I use R to be M, then I'm not doing any dimension reduction. Then I can get back the exact matrix V without doing any dimension reduction, but that's not what we want to do. We want to reduce the dimension, so we want to choose an R that is smaller than M. So we are trying to approximate the matrix V by the product of two matrices W and H, right? So our original is phi, our approximation is W times H. This W is called the basis matrix, and the matrix H is called the mixture coefficient matrix, because its column vectors correspond to the weights or the coefficients that are used in the linear combination of the columns of the basis matrix. So let us look at the overall idea of how we perform this factorization. So we start with a matrix V, and then we decide that, hey, we are going to use a factorization rank R. That means our W matrix is going to have rank R. Then the first step would be to come up with some initial guesses for W and H, right? Since they're the initial guesses, we're going to call them W with a suffix 0 and here. So these are the first time points, or 0x time points. Then, based on certain algorithms, we are going to update the value of W and H so that the values of W and H become closer and closer to V when we take the product of W and H. So we need an objective function. That means we need to be able to quantify how close the product of the matrices W and H, which I'm going to call WH from now on, how close is the matrix WH to the matrix V. So we need to define a loss function. So often this loss function is based on the usual Euclidean distance, or often used, often a generalized Kullback-Leibler divergence is used. So, but at the end of the day, the idea is that we are trying to track how good we are approximating V using W times H. Now, the ideal scenario would be to keep doing this until the approximation is so good that the approximation error is less than certain threshold. But often the computational effort is too high. So we fix the number of iterations, say 100 or 200 or 1000, depending on your computational power of your machine. Next thing that is important is initialization. How do you choose the initial values of W and H? Well, right now in R, it does it for you, but we should know that there are three important techniques that are used to initialize. For example, clustering techniques. You can initialize the basis matrix using the, say, taking the centers of the k-means algorithm. So you take the data, you cluster it, take the cluster means, and they form the basis matrix. Because we assume that when we perform clustering, the clusters are as different as possible from each other, right? So they become the basis. And the mixture coefficient matrix can be initialized as a proper scaling of the cluster labeling matrix, or the cluster indicator matrix. So there are many other options, but they are inbuilt into R. So, but we should know that it is an important choice, the choice of initialization. Next is the choice of rank. What rank should we choose? Well, the idea is that once you choose an R and you perform all the updates of W and H and you reach a final value of W and H, you can look at the approximation error, V minus WH, and see how well you performed. As you change R, you can track how much approximation error you are doing. Of course, as you keep increasing R, your approximation error is going to always decrease. So you can use an elbow method or an inflection point to see the point beyond which you are increasing R, but the increase in, or the reduction in error, approximation error, is not significant enough. So it's like the elbow method that we have talked about earlier. Next, we are going to talk about a little quiz before we move on, where we are going to see if we remember the properties of non-negative matrix factorization. So here's a question here. And we're going to load this quiz and just try to remember if this is true, that when we try to factorize the original matrix V into two matrices, are the two matrices W and H also supposed to be non-negative? I'll give you guys a minute or two to try to absorb the information that we just discussed and then try to understand this. All right, thank you very much for participating. And the answer is, it's true. W and H are also non-negative. That's the way it is factorized. So before I move on to the applications in R, any questions, or do you want me to go through certain concepts again, or just give a brief summary of the overall concept? Any questions, just let me know. Okay, I'll give you 2 minutes to ask me any question. Just try to absorb the information. The idea of taking a matrix. Right, yeah. Maybe I will do the summary, yeah, okay. Any other questions? I will do the summary, but any other questions? All right, in that case, let me just, okay. That's a great question. That depends, right? That depends on what's your choice of the number of principal components, what's your choice of the the rank of the non-negative matrix factorization. They are both do the same things. They both try to reduce their features. And we are actually going to look at an example, if time permits, that where we do PC and non-negative matrix factorization on the same thing and see how their performances measure up. And if the coefficients and the data are positive, you will get very similar results. But you cannot really draw a comparison between the K which controls the number of principal components, and R, which controls the number of non-negative matrix factorization. So, I mean, P and K are not very easily compared, right? But you might get a very similar output, yeah. And that was a great question, by the way. And we are actually going to cover it if time permits. So let me just quickly summarize what we have, and let's get there then. Okay, so let us try to see. We have a matrix phi with, say, a lot of columns, a lot of entities, okay? We are going to reduce the dimension by representing this phi by this same matrix, but not by this huge matrix V, but as the product of two matrices, W and H. This W has a rank R, which means its dimension is smaller. So we are doing reduction of dimensions. And H is of dimension R, R cross M. So it has a lesser number of rows. So we're reducing the dimensions. We have two new matrices, W and H, which we are going to use to represent the original target matrix phi. Now, the two matrices together, W times H, perform an approximation of V. So if I use the entire data, if I did not do any reduction, dimension reduction, then, well, W times H, we can find a W and we can find an H, so that W times H is exactly equal to V. But we don't want that. We want to reduce the dimension, but we also want to capture as much of the information in V as possible. So we take R, and based on the choice of R, you have the amount of information that you are extracting. If you take R to be too small, then you do not capture most of the information in V. If you take R to be too large, then you capture most of the information, but you are not reducing dimensions. So you have to find a sweet spot. So in an algorithm, we have a target matrix phi, and we need to find two matrices W and H so that their product is an approximation for phi. So the first step is find an initial guess for W and H. So that's the initialization. Next, how do we measure the approximation? We need an objective function to quantify how close is the W times H matrix to the original matrix phi. That is the only way we are going to realize if we are doing a good job of approximating the target matrix or not. Okay, once we have done the initialization, there are many ways of updating the values. That depends on various methods. Several papers have come up with several different methods. We're going to see several options in R, and we're going to choose one of them that uses the Euclidean method. Next is the choice of rank. As I said, we have to find a sweet spot. So looking at the elbow graph tells us what is a good choice of the rank. So once we have figured out the way to find the objective function, to evaluate the approximation, once we have figured out a way to initialize the matrices and a way to update them, then once we have finished updating them, then we have a W final times of H final, which we then take a product of, and that serves as an approximation for the huge matrix phi. And that is the idea of non-negative matrix factorization. We are factorizing the matrix V into two matrices W and H. That's the idea. Is that clear? Does it make sense? Or is there any part that you would like me to explain again? Guys, it's clear? Let me know if you're clear and I can move on. All right, I'm going to assume that you guys don't have any questions right now. So let us move on to the application to iris data. Well, first of all, running this is going to take quite a while. So be prepared for this. So the imager package deals with image processing. And we're going to use the package NMF within the biobase, which performs the non-negative matrix factorization. Okay, so we load them up. And the first thing we do is we're going to use the non-negative matrix factorization on the iris data. So our data is just the first four columns of iris. And we're going to use a rank equal to 2. And we're going to use a method equal to Lee. So there are different methods, different algorithms for initialization and updates. So they are, each of these methods corresponds to different methods that are discussed by the corresponding papers. I have used Lee here because it uses Euclidean method, and it's as good. It's very nice. So the next argument is dot options equal to P3. That means it requests for parallel computation if available. So P3, the 3 stands for request for 3 CPU. But if parallel computation is not possible by the system, then it performs usual sequential computation. But if you want to force parallel computation, you can make the P capitalized. And then if parallel computation is not possible, then this line of code is going to give you an error. All right. Next is how do you choose the initial values? And that is chosen by NFF seed. These are different options. Seed equal to 1, 2, 3, 4 means we're choosing a random seed. Okay. Now this NMF fit object A has a lot of properties. If you want to find the approximate target matrix, that means the V that is now approximated, that can be obtained by the fitted function. So if you do fitted of A, then you will get the fitted values. Okay. If you want the H matrix, the coefficient matrix, you do dot COEF of A, then you get the coefficient matrix. And if you want the W matrix, then you do dot basis of A, which gives you the basis matrix. All right. So based on the NMF object, you can extract whatever information that you need here. So let us try to find an interesting application into image analysis. So this image, it's a brain MRI. It's a weighted sequence. So we have 3 different images here. And we can load this image using the load.image function. And we can plot it. So here, I do not know if you are familiar with this notation or not, but this percentage arrow percentage, this is a piping function. This basically means that you take this object, RGB image, and then on this object, you perform the function that is mentioned in the next line. So in the usual notations, it would be same as doing plot RGB underscore image, comma, axis equal to false. That's the usual way of how we plot it. But this notation is very handy in trying to pipe different actions one after the other. So next we're going to convert this image to a grayscale image from an RGB. RGB stands for red, green, blue level image. We are going to convert it to a grayscale image where we have values from 0 to 1 corresponding to the grayscale value of the pixel. So the grayscale function is used to convert this image to a grayscale value. Then we can look at this image as a matrix to get the value of the pixels as the matrix entries and the locations corresponded by the row and the columns. So if you look at this rank, the original matrix has 233 dimensions, okay? 233 dimensions, that's a lot of dimensions. So let us try to see if we can reduce it and still have a clear picture. So we are going to do non-negative matrix factorization and use rank equal to 10, method equal to Lee, and the rest of the options are it is. So we are going to use the gray image mat. That means the matrix version of the gray image. Now, once we have this, we are going to do the fitted of NMF. Remember that fitted gives you the approximate target matrix. And then as.cimg converts this matrix to the form of an image. As.cimg converts a matrix to an image. So basically, we reduce the dimension to 10, r equal to 10. Then we use the fitted function to get the approximate target matrix, and we convert it to an image, and then we plot it. And this is what it looks like. As you can see, it's not clear. I mean, it's not clear to me. Maybe graduate students from the biomedical major can tell me more if this is clear enough or not. But at least visually, it doesn't look like this is enough. Because remember that at the point of the day, using this image visualization, we would like to be able to do classification down the line. We want to take different images of different cells, maybe belonging to different groups of patients, and try to find a classification or difference, right? So we need to be able to differentiate across different images. If our image is too blurry or does not have enough information, then we will not be able to do that. But what happens if we reduce from 233, not to 10, but to 50? How about now? Much clearer, right? Much clearer. So all I have done is I've changed the rank from 10 to 50. And we see that these images are quite clear. And if you want to say these three images were three different things that we wanted to separate out, then we can clearly see the differences across the three images. Here, between A and C, there is a lot of similarity. It's not so clear. The differences are not so clear. It's not very well separated. But these large areas here, they are much more clear, using only rank equal to 50, where the original was 233. So that is the power of these methods. So before I go to the optional topic, the optional topic is basically quite an advanced code. This code is performing PCA on the same image, and we're going to see how the PCA performs on the same image data set. That is going to give you an idea or at least an experience looking at codes that perform image analysis. And if you can see, you can try to mimic this code to perform PCA on images and see how the reduced dimension images look like. And if you can use them for classification or clustering. So before I move on to the optional topic, any questions? And if not, just send me it's clear or something. does the non-negative matrix factorization, this concept, make sense? All right, if you do not have, do you have? Sure. Well, let's see. So if you are looking at the codes, then I would say look at the nmf.pdf that's in the CRAN R project. They have a very good vignette, and you can look at the functions. But if you would need some materials, then I need to search for it. I don't have them right now. So feel free to send me an email later and I can share some references with you. Okay. All right. So Michael, just send me an email and I'll share some references with you. And let's look at the optional topic, that is the code performing PCA on an image. Now, this code is quite involved, but all I want you to do right now is just get an overall idea and look at the final reconstructed images, just to have an idea of the performance of PCA. So we are going to install these 3 packages here. Do not worry about these packages. I mean, you have to install them, but remember that it might take some time. So we have loaded the image exactly as before, and we have converted to a grayscale image. And then I've looked at it, the grayscale image, im_PCA, as a data frame. And this is what the data frame looks like, X, Y, and the pixel, the grayscale intensity values. Next, I'm going to use the function pivot wider. What does the function pivot wider do? Well, it takes a matrix, or it takes a data frame, and it increases the columns. It's called a wide format, which is used for forming PCA. Okay. This format here is called, this double colon represents that I want to use the function pivot wider of the tidyr package specifically, because often it so happens that when you have a lot of packages loaded, a lot of packages have the exact same function name. And so that confuses R which one you want to use. So a lot of functions get masked. So this tells R that I want to specifically use the pivot wider function in the tidyr package. That's what the double colon does. So we spread out the columns. So this is a usual long format. We're going to make it a wide format by spreading out the Y values and put the values from the value column. So now this dimension is 640 rows and 234 columns. So it's a wide one. Now we are going to use the PCA. So notice this piping thing. we have this data stored in a wide format in img_df, right? On this image, once you store it in the wide format, the first column is always the row IDs. We do not want to deal with that. So we remove the row ID. The name of the column that contains the row IDs is always X. So we do that. We want to select -X. That means we're removing that row ID column because we don't want to deal with that. And then we are going to perform PR_comp. That means the PCA with scale equal to true and center equal to true. Now, if you did not use this piping format, you would have to do PR_comp of select of -X of img_df. So it's much more convenient to pipe the functions, and that tells you exactly what function you are doing at each step. Next, we're going to look at the summary. Now, this summary is the most interesting part, at least for me. So we have this image, and we have split it up into several principal components, 233 of them. Because 233, because we removed the first column, remember, so we have 233, not 234. All right, so let us look at the proportion of variance, because that is what we're interested in. But let us focus on cumulative proportion, because we are going to combine the first few anyway. So if I use only the first principal component, I explain 52% of the data. If I use 10, I explain 86.6% of this data. If I use 45 or 46, I explain more than 99% of the data. Note that there are 233 dimensions. And by 46 dimensions, we are explaining already 99% of the data. Good. So this function is a very involved function, but all it does is it reverses the PCA. Remember, we took the original data, we put it in a wide format, we normalized it, and we scaled it, and we performed PCA to get the transformed values. That means the PCA values. This function, our reverse PCA, simply retraces its step back. So the first step is we are going to move from the PCA values to the original values. So we are going to multiply the PCA values by the transpose of the rotation matrix. Remember, the rotation matrix had the original variables in the rows and the PCAs in the columns. So if I do the PCA times the transpose, I can get back the original variables. But we are not going to use all the PCA values. We are going to use only n-comp of them with the default value 20. Default value 20 to get back the original variables. Next, we are going to scale them. So we are going to unscale them basically and uncenter them. Okay. Next, remember that we had changed the data from usual format to a wide format. So we have to return it to the long format using the opposite of pivot wider. It's the pivot longer. Also, remember we had removed the first column. Remove the first column that contained the row IDs. So we are going to add it back. So all this function does is it retraces it back so that we get back the original data format, but using only n-comp principal components. That is the only difference. So what we're going to do is we're going to take several number of PCA components. We're going to see 2 to 5, 10, 20, 50, and 100 and see how it performs. The remaining part of the code is simply applying the function reverse PCA on these numbers, using these numbers as the number of principal components, and then plotting them. There is no need to go through these codes right now. You can go through them at your own time, but look at it. When you have up to five components, it's not very clear. When you use the first 10 components, I would say this is a clearer version than the non-negative matrix factorization, right? I think the left one and the right one are more easily separated. I can see the differences more clearly than the than this one here, I think. But it's up to you. So that is what I mean by saying that the rank value 10 and the k value 10 might not be exactly the same thing. But when you use, say, 20 or 50 components, it's already extremely clear because we have explained more than 99% of the variability of the data. Okay. So I have another image here. It's just an image of the Mount Rushmore. Try to see if you can mimic these codes and perform a non-negative matrix factorization and PCA at your own time. Or I would say that if you have any biomedical images, try them. It's very exciting to try to see the power of these dimension reduction techniques and see if you can perform classification once you have done the dimension reduction. So that brings us to the end of this lecture. So any questions? If you have any questions, just ask me right now. You can ask, I'll answer them. Any questions throughout the entire presentation? If you have any clarifications or any explanations that you need, let me know. So here is a reference for, let me check. Right, I think session 4 and 5 are available. Session 6 had a lot of technical issues because of Zoom things. So it's taking some time to load that up. So by the way, Michael, here's a nice paper that you can read regarding the non-negative matrix factorization. So if you do not have any questions, then I would like to thank all of you for joining in and learning dimension reduction with me. And I'm going to hand it over to Christina.
Thank you once again, Dr. Dasgupta, and thank you all for joining us. As a reminder, our next session is going to be on Wednesday, March 9th from 1 to 3 p.m. And that will be session 8. And our topic is Fundamentals of Fair Research Data. And our presenters will be Dr. Watts and Sari from the library, as well as Dr. Tabor from chemistry. If you have not registered already, please do so, and we will hopefully see you on March 9th. Thank you.
Thank you so much, everyone.